Hey there, today we're going to look at vectors in the plane. In this section we will study two-dimensional vectors, vector operations, unit vectors, directional angles, and a few applications. A vector is a directed line segment that has magnitude and direction. Velocity is an example of a vector. We use an arrow to represent a vector, and the magnitude of a vector is the length of the line segment. The arrowhead indicates the direction of the vector. So in example 1, we're going to look at linear combinations, component form, standard position, and translating a vector given 2 points. So let's get started. If we have the point 4, 1, and that's point P, and we have the point 7, 5, that's point Q, and it represents a vector from P to Q. I could put a little arrowhead on that, I guess, from P to Q. We want to move that vector back to the origin. So the easiest way to do that is to subtract or take the displacement or the difference between the x coordinate, so this coordinate and this coordinate, the x's, 7 minus 4, and then the difference between the y's, 5 minus 1, and we can translate or move that vector back to the origin. So if I say z is my component form, is my component form, here's how we write component form. Here's linear combination form. Then I could pick that vector up and move it to 3, 4. And I'm going to show you how that looks with my directed line segment. So here's my vector. And you can tell if I pick this vector up and move it 3 units to the right, 4 units down, I'm going to be right there. Right, from P to Q. So we've moved that vector back to the origin. This is called standard position. Or I'm sorry, this is called component form. And then if we write that vector in linear combination form, then that vector would be 3 in the I direction and 4 in the J direction. So the x-axis, now don't confuse this as polar form like we did in the last lesson. I is the x-axis and J is the y-axis, and they represent a unit vector. So I went 3 unit vectors over on the x-axis and 4 unit vectors over on the y-axis. I'm in the wrong spot here, right? 4, 1. I'm sorry, I went 4 unit vectors over on X and 1 unit vector on Y, and then 7 unit vectors on Q on X and 5 unit vectors on Y in order to get to those points. We'll see more about that in a bit. When we add vectors geometrically, the sum of 2 vectors can be defined by the tip to tail rule. And that rule says if I have the position of vectors u and v, so that the terminal point, which is the arrowhead, the terminal point of u coincides with the initial point of v, then the vector u plus v is formed from the initial point of u, that's the initial point right here, to the terminal point of v. So getting my arrow tool out or my vector tool out, that from here to the terminal point of V is going to be the sum or adding the 2 vectors u plus v. Now you can also see that this creates a parallelogram. So if we did vector v, went 1, 2, 3, 4, 5 up and 2 right, starting here, 1, 2, 3, 4, 5 up and 2 right, this vector is another translation of v, and then vector u is 1 down and 1, 2, 3, 4 right. So 1 down and 4 right. This is vector u, another translation of vector u. It creates a parallelogram, and the diagonal is called the resultant, or the sum of the two vectors. So tip to tail is the approach. Here for u plus v, if we add u plus v, following that same rule, then the terminal point of u is the initial point of v, and the sum of u plus v goes from the initial point of u to the terminal point of v. So there's our u plus v in parentheses. And then we want to add w to that. So the beginning, let me see if I can shorten this up so you can see the arrowhead there. So to add u plus v would be the initial point of u plus v ends at the initial point of w. So to add u plus v plus w, we would go from the initial point of u plus v to the terminal point of w. So this becomes, this line across here becomes u plus v plus w. If we're going to do v minus w, let's see, what was v? V went 5 up, so we'll come down here and go start, let's go look at v. V was 1, 2, 3, 4, 5 up and 2 right. So I've got to draw v. 1, 2, 3, 4, 5 up and 2 right. So there's v. And then w was 1, 2 down and 3 right. But we want to go the opposite direction because it said subtract w. So we want to go 2 up and 3 left. And that would be subtracting w, or the opposite direction. This is v, and this is the opposite direction of w. So with my arrow again, the end of w and the beginning of v becomes v minus w. Okay? And then we got one more to do. Actually, we just drew that one backwards, didn't I? I said the initial needs to be, let me back up here before I get you confused. So where v starts, the initial point of v to the terminal point of the opposite of w. I started at the top and went back. That was wrong. So v minus w, our arrowhead's up here. V minus w, because v started and then the initial part of w going in the opposite direction of w, since w is supposed to go that way. Now we're going the opposite way. Go back to the initial and go across to the terminal. Okay, and the last one is v minus 2u. So v began, we'll start v down here, go 1, 2, 3, 4, 5, and to the right 2. So v, vector v, is right here. And then we want to go in the opposite direction of u twice. So u went 1 down and 4 right, so we want to go 1 up and 4 left, and then we want to do it again, 1 up and 4 left. So we have the opposite of u once and then we have the opposite of u twice. So this is v, and this is the opposite of u and the opposite of u. And using our line tool or our vector tool, from the initial point of v to the terminal point of the two u's, then we have v minus 2u for our vector addition there. Okay, on example 3, next we're looking at magnitude of vectors. So magnitude, again, that's the length of the vector, and we saw magnitude or absolute value in the last lesson. It's the same thing. We're finding the hypotenuse of a right triangle, if you want to think about it that way. If vector v is represented by an arrow from one point to another point, then the distance formula is how we find the magnitude. And if we have component form, then the magnitude is still the A component and the B component. So let's say we want to sketch and find the magnitude for -2 in the x direction and 3 in the y direction. So do you get the idea that the I and the j, they're just a unit vector? There's one unit vector, 2 unit vectors, and then we're going to go 1 unit vector, 2 unit vectors, 3 unit vectors. So that's where the I and the j come from. So this is the end of our vector, and if we used our vector arrow tool and draw the terminal side, you can see that you have a right triangle here. If you just imagine dropping the perpendicular back to the x-axis. So our vector in component form is -2, 3. This is linear combination form. And the magnitude is the square root of the A term and the square root of the B term squared, the square root of the sum of the A term and the B term squared. Whew, got my words jumbled there. So -2 squared and +3 squared gives us the magnitude of radical 13. And that would be this length here. And we don't have any units, so radical 13 is our magnitude. There's some properties. I won't spend too much time, but you can come back and review those as you need them for homework. And we're going to operate on these vectors using those properties. So if I multiply 2, 2 is a scalar. It just increases the size of vector v. And then I want to add vector w. So it's pretty simple arithmetic. I can distribute the 2 and increase the size of this vector. But then when I want to add the component forms together, I want to add the x term to the x term, and then the y term to the y term. So we get a brand new vector, vector addition, -4 and 14. And then here if we find w minus v, we have 2, 4 for w, and we're going to go the opposite direction of vector v. So using distributive property with the minus, we can turn that into addition. This becomes +3 and then -5. And then doing the operations of the x terms and the y terms together, we find out that our component form for the sum of the difference of the two vectors would end or terminate at 5, -1. So operations on vectors. Then here's where we're going to look at the unit vectors. A unit vector is any vector whose length is 1. So we're establishing the 2 unit vectors on the axes as 1, 0. So if we come out here to 1, this vector along the x-axis is vector I. And if we come up here to 1 on the y-axis, then the vector from the origin up to 1 on the y-axis is vector j. So we want to find a unit vector in the same direction as 3, -4. So if you think about the look of that vector, we're coming 3 units to the right and 4 units down. So this vector from the origin terminates at that point 3, -4, which means the hypotenuse is going to be square root of 25, since a squared plus b squared is the square root of 25. So the length of this vector is 5 units long, and our job is to find the unit vector. So you find the unit vector, this needs an equal sign in there. You find the unit vector by taking the vector itself, which is 3, -4, and we're going to divide it by the magnitude, and the magnitude is 5, or the length of that vector. So our unit vector in the same direction as vector v is going to be 3/5 and -4/5. Now, what does that mean? That means that I should have 5 vectors that lie along this line, 3, 4, 5, and each of those vectors are the same length, but this first one terminates, that end point right there is 3/5 to the right and -4/5 down. So that's called a unit vector. Then we have, let's see, did we skip the equal vectors? On my notes I have equal vectors. Components of a vector. Anyhow, 2 vectors are equal if their components are equal. So you can have equal vectors that are going in the same direction, the same length. In components of a vector, there it is. 2 vectors v and w are equal if and only if their corresponding components are equal. So if vector a, b, and vector w, a, b, then they're going to be equal only if the a terms in each vector are the same and the b terms in each vector are the same. So in lots of applications, a vector is described in terms of its magnitude and direction. A velocity vector is any vector that represents the speed and the direction of an object, but a force vector represents the direction and the amount of force that's acting on the object. So in order to model velocity and force with vectors, we have to be able to find the horizontal and the vertical components of a vector. So the components of a vector, see, this is similar to our polar form. We have A is magnitude times cosine and B is magnitude times sine. Now, in our last lesson on polar coordinates, if you had a polar number that was r and theta, you can kind of see how they're related. R was our magnitude or absolute value or modulus. So it's just different language, but it's the same concept that for this direction you can create some kind of a right triangle. And polar form only had a real axis and an imaginary axis, where in vectors we have two axes that are both real numbers. I is in the horizontal direction and j is in the vertical direction. So we just have to keep all of that terminology straight. In example 6, a vector whose magnitude is 6 and is in the direction of -3, +3, we're trying to write a new vector. So if we go -3 to the left and +3 up, we have a vector here that is a shortened version of our vector we want to have magnitude 6. So we're looking for the endpoint of some vector out here so that the distance from here to here is 6. We're trying to create that. And that's our task here. So first things first, we want to find what is the magnitude of this vector and what's the direction angle that it's heading in. So similar to last time, I could find that the direction is going to be the tangent of the y value, which is 3, over the x value, which is -3. So the tangent inverse is going to give me that angle, and that's where tan inverse is -1. So -1 is going to be -45 on the calculator, but I can tell by looking at it, if I add 180 to it, I'm at 135 degrees. So we want a vector that's 6 units long in that same direction. So to make it 6 units long, that's my magnitude. So my new vector is going to be 6 times cosine 135 in the I direction plus sine times 135 in the j direction. And I put the 6 out in the front. So there's my linear combination. Well, there's my vector in AI plus BJ format, but I want to write the linear combination of that. So the linear combination would be similar to our last lesson. What was the cosine at 135? And then multiply that, and then times 6 again. What was the sine at 135? That would be positive in quadrant 2. So our linear combination would be -3 square roots of 2 in the x direction and +3 square roots of 2 in the y direction. So if you wanted to have some kind of a number sense for that, to see exactly how far, that's about 4 1/4, close to 4 1/4. So if we came out here just a little bit more and go up about 4 1/4, this new vector from here to here is going to have a magnitude of 6. So a little bit longer than the one that we started with, but not much. Okay.